Hello, team. Thank you. One quick thing before I start what I was going to do. At one point, I gave you this. You have this already, you don't have to write it down again. And then I said if dr is equal to 0.1, essentially, what is dv? Yeah? And I wrote that like this. And then I took the derivative. Yep, and that uses the definition of the differential. As I mentioned to at least one of you, and I think I mentioned this briefly in class, you could, if you have trouble remembering this, and you like the Leibniz notation, you could just write dv by dr, the derivative of v with respect to r, is what? 4 pi r squared. And then you can now think these are separable things, and you can just rewrite that as this, by multiplying both sides by dr. Okay? So if you have a lot of trouble remembering this, just do that. And presumably that's a forgivable thing to do. Okay? Awesome. Okay, I intend to talk about indeterminate forms. I'll do a Newton's method example. I'll mention implicit differentiation. I'll mention something else, and then I might do a related rate thing. Okay? 2 of these are upon request, or by request. Here we go. Okay, what I'm going to do is I'm going to continue what I was doing this morning, and then I will only briefly summarize it on Wednesday. Threatening silence. All right. No, you can't see any of this, can you? Ta-da. Excellent. Okay, we've seen this. I put this table in to tell you what the indeterminate forms were. This might not be worth copying down, okay? It should be clear enough what each indeterminate form means. Like if I say 0 over 0 means the top and the bottom are going to 0, okay? I just put this in for clarity. If you're confused about something, check this or ask me. But this isn't really something that's worth writing anywhere. But my time has no value, so I just do stuff like that. Okay. All right, so we did sin x over x, both with linearization and with L'Hopital's rule. And I said that we were essentially cheating by doing that. And now let's do another example. Ready? Okay. Okay, this is going to be indeterminate forms. Continued. And here we go. For example, we want to evaluate the limit as x grows of ln x over the square root of x. Okay, where's the top going? Anyone? Thank you. Good, where's the bottom going? Perfect, okay, good, okay? As x grows, ln x, which looks like that, is growing, albeit slowly. Square root of x is growing, albeit slowly, and they both grow ultimately without bound. So the top is growing without bound, and the bottom is growing without bound as x grows. Okay? And I'm writing this so that we don't screw up. We don't think that something's indeterminate when it's not. Okay? So this is indeterminate of type infinity over infinity. Okay. And L'Hopital L'Hopital is kosher for that. So let's do it. Use L'Hopital's rule, which says take the derivative of the top, 1 over x, take the derivative of the bottom, however you figure it out, is 1 over 2 root x. Just make sure I'm not doing the wrong part of this. Okay? Good. Took derivative of the top, took derivative of the bottom. If this is really unfamiliar to any of you, let me know. Okay? At this point, you could say, that goes to 0. That goes to 0. So that's 0 over 0, so I'll do L'Hopital again. Okay? Well, you shouldn't do that. Okay? So again, you could note that this is going to 0, this is going to 0, so this is indeterminate of type 0 over 0, and then do L'Hopital again, okay? Or you could be smarter about it and do this. Just rearrange this. This becomes... Can y'all see that low? Okay, if you can't, complain. Okay. We got 2 over root x. Okay. Again, what did I do? I noticed they both go to 0, and it's type 0 over 0, but instead of using L'Hopital's rule, I can kind of end the thing here rather than going on for ages. So I rearrange this thing. If you're confused about that, let me know. Simplify to that. Okay, 2 over the square root of x. And I already know that that's 0. And that's it, okay? How do I know this? Because 1 over x to the anything positive, as x grows, is going to go to 0. And 1/2 is positive. Okay, good. So, ta-da. Okay, very slowly approaching 0. Okay, so 0 is a horizontal asymptote of this thing, or y equals 0 is a horizontal asymptote of this thing. Okay. What is this saying? We're saying this ratio is going to 0. Okay, so we're saying that ultimately, this guy outstrips this guy by as big a percentage margin as you can imagine. Okay, so any percentage margin you set, this guy will beat this guy by that and more. Okay. In other words, we have a little tug of war between these two guys. Okay, they're both going to infinity, or they're both growing without bound. This guy wins the tug of war. Okay, and that's why your answer is 0. If this guy won the tug of war, your answer would have been infinity. Okay. In other words, this guy increases ultimately faster than this guy. And you may remember at some point I said logarithmic functions grow much, much, much more slowly than power functions, including root functions. Okay? And I put up that picture ages ago. Maybe I can do this. Okay, I put up this picture ages ago to show you that the logarithmic functions ultimately grow much more slowly than the root functions. Okay? Though again, you sometimes have to zoom out quite a lot to be able to see that. Okay, so that was an example of it, and you can very easily show using L'Hopital's rule the same thing for any n. Here we did it for n equals 0.5. You can easily do the same thing for any positive n. Okay? Prove that log grows much, much, much more slowly, arbitrarily more slowly, than any power function. Okay? With positive exponents. Is that okay? Okay. Again, logs are slow. Okay. Okay, almost the same example, with the axes flipped essentially. So now we're going to find the limit as x grows of e to the x over x. It's been a while. Over x squared. Okay? Same deal, as x grows, this guy grows without bound, this guy grows without bound. Okay? So this is indeterminate of type infinity over infinity. Okay? It's indeterminate, meaning we can't figure this out just by knowing that the top blows up and the bottom blows up. We need more information than that. We need to do something else. So we use L'Hopital's rule. Derivative of the top is nice. Derivative of the bottom is almost nice. And we get that. Yeah? It's a bit better, but it doesn't give us our answer. The top goes to infinity as x goes to infinity, and the bottom does the same. Okay, we have type infinity over infinity again, so we can use L'Hopital again. Derivative of the natural exponential is itself again, and derivative of 2x is just 2. There we go, life's good, okay? We know that that guy grows without bound as we go that way. And there's our answer. Okay, so one of the lessons here is that you can use L'Hopital's rule multiple times. Okay, but if you find yourself using it 10, 12 times and you're not getting anywhere, maybe try something else. Okay? All right. Good. And again, this was essentially that with the axes flipped, right? Instead of square root x, we were talking about x squared. Instead of ln x, we're talking about e to the x. We're essentially talking about the inverses of these things. Okay? So these are two sides of the same coin, really. The fact that we've got an infinity here, first of all, we have the graph. Okay? Looks fair enough, right? As we go this way, this thing's blowing up. So that makes sense. And what are we saying here? Again, we have a tug of war. This guy's going without bound, this guy's growing without bound. This guy wins, okay? And that's why we get an infinity here. If this guy had won, we would have gotten a 0. If they'd compromised, we might have gotten something else. Okay, so that guy wins. And that's it. And again, another way to say that is the exponential will beat any power function, in particular that power function, by any percentage margin eventually. And at some point, I told you that exponential functions grow very quickly, and they ultimately grow faster than any power function. And again, using L'Hopital's rule, this kind of thing, you can just repeatedly use L'Hopital's rule to show that fact for any positive integer n. And you can extend that to any positive number n. Does that make sense? Okay, exponentials kick butt. That's the lesson there. And logarithms don't. Okay, good? Okay, so let's do this now. Who can't see that? Is anyone who can't see that? So I don't have to turn the lights off? Okay. All right, indeterminate products, which are also indeterminate forms, but a special kind. Indeterminate products. Up to now we were talking about quotients. For example, the limit as x approaches 0 from the correct side of x ln x. All right, what's going on here? As I approach 0, x approaches 0. And ln x goes like that. So ln x goes down. Okay? We call this kind of thing an indeterminate form of type 0 times infinity. If you write 0 times minus infinity, that's cool too. Okay, good. And that kind of form is in that table, so if you feel like you can get a table, go ahead and do that, but it's not really necessary. Okay, so what's going on in this product? This guy is trying to pull the product down to 0. This guy is trying to pull the product to minus infinity. Okay, again, tug of war. Who wins? If this guy wins, we'll get a 0. If this guy wins, we'll get minus infinity. And if there's a compromise, we'll get something in between. Okay, or nothing. Okay, so there's the rule. This is what we're going to do. So whenever we have an indeterminate product, because we're not going to be very creative, we're just going to try to rewrite it as an indeterminate quotient. Okay. So here we go. Let's rewrite this thing. Okay? Instead of f at x times g at x, or maybe I'll switch it around to make it match that. Instead of f at x times g at x, we'll write f at x over the reciprocal of g at x. Okay? And you can pretty quickly convince yourself that if you have an indeterminate product of type 0 times infinity, and you do this trick, you'll get an indeterminate quotient of either 0 over 0 or infinity over infinity. Okay? If you're unconvinced that that's the same as that, let me know. Okay, as we go to 0, this guy goes like that. As we go to 0, this guy goes like that. Okay? The signs can be whatever they want. We've got infinity over infinity. And now we're in good shape to use L'Hopital's rule, which is nice. So it's this old trick. Rewrite the thing to get something you recognize. Okay? All right. L'Hopital's rule, take the derivative of the top, 1 over x. Derivative of the bottom is minus 1 over x squared. And now again, conceivably, you could go, okay, well that's going to some kind of infinity, that's going to some kind of infinity, and I'll use L'Hopital again. Not a good idea. Okay, instead you can settle it right here. So let's end it now that we can. Okay, rearrange that and you get minus x squared over x, or just minus x. And as x goes to 0, minus x goes to 0. Okay? In other words, x won the tug of war. It succeeded at dragging you down to 0. And I think I have that there. Okay, and there's your picture, as usual. Okay, as I approach 0 from the right, I'm approaching 0, which is what that said. Okay, you could have tried writing this as x over the reciprocal of ln x, and your life would have been very difficult. Okay? So you can try that and see that it gets hellish. And once things get that hellish, you might go, okay, maybe it's the other way around. Okay, so instead of taking the reciprocal of ln, sticking it down here, I'll do it this way. You see what I'm saying? Okay. So if we try doing this the other way around, it'll get difficult. And when things get difficult, give up. You know what I mean, yeah? Try something else as well. Okay. Excellent. Okay, that's that. Okay, indeterminate differences. And this is the last thing we'll do. There's also powers, but we're not doing that. If you're interested, tell me. Okay, our example is this. Very painless example. Limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. All right, so what's our problem now? As we approach 1 from the right, ln x approaches 0 from above, and so this guy goes to infinity. And as we approach 1 from the right, this guy kind of looks like that. It's going the same way. It's going to positive infinity. Okay? And guess what I'm going to say? It's an indeterminate form of type infinity minus infinity. Okay, so if ever you've got the same kind of infinities being subtracted, quote unquote, you've got a problem, you've got that kind of problem, what do you do? Okay, and again, you've got a tug of war. You've got this guy trying to pull you up to infinity, and you've got this guy trying to pull the difference down. So does one of them win, or do they compromise? And again, total lack of creativity. We're just going to try to rewrite this as a quotient again. Okay, a bunch of ways of doing it. Common denominator, factoring. Multiplication by conjugate, or substitution. And in this case, it's the easiest one, just common denominator. Okay, so, you see that? What are you going to do? The dumbest possible thing and the easiest possible thing to do is to just rewrite it as follows. X minus 1 minus ln x. Okay, so you put both of these guys over the common denominator of x minus 1 ln x, subtract them, and you get that. Okay? And now look what's happened. As this guy goes to 1, this guy goes to 0, this guy goes to 0, so the bottom's going to 0. This guy's going to 0, and this guy's going to 0. Hey, would you look at that? Okay? So, indeterminate of type 0 over 0, and we recognize it, and we're happy. Okay, so use L'Hopital's rule. Export. Okay. Okay, L'Hopital's rule. Derivative of the top, 1 minus nothing, minus 1 over x. What do we got here? Derivative of the first is 1 times the second ln x plus the first times the derivative of the second, which is 1 over x. Okay? Recognize the type, use L'Hopital. All right. Let's just rewrite this a bit. X over x is 1 minus 1 over x. Let me just see which way is hairier. I'll just do this. All right, look at this guy now. As we go to 1, this guy goes to 1, the whole thing goes to 0. 0. As x goes to 1, this guy goes to 0, to 1, to 1. 0 plus 1 minus 1, going to 0. So you're either happy or you've grown because we've got a L'Hopitalable type, and we take L'Hopital's rule again. Okay. Okay, nothing minus 1 over x squared, so on the top is 1 over x squared. That's just power rule. Okay, derivative of ln x is 1 over x. Derivative of 1 is nothing. And again, we got minus 1 over x, whose derivative is plus 1 over x squared. Cool? Excellent. Now we're happy. Everything's good. The top goes to 1 over 1 squared, or 1. The bottom goes to 1 over 1 plus 1 over 1 squared, or 2. 1 over 2. Essentially by substitution or limit laws, however you want to think about it. And there you go. As we're approaching 1 from the right, we're approaching 1/2. Life's good. Okay? If you wanted, once you got this, instead of using L'Hopital directly, you could have multiplied the top and bottom by x, if you feel that that's prettier, and then proceed from there. Do L'Hopital from there. Okay? Again, multiply top and bottom by x, simplify a bit, then do L'Hopital, and you get the same answer. If that looks cuter to you. Okay. All right, that's differences. Any questions? There are other methods. Maybe at some point I'll show you some of the other methods. Or maybe you'll see them yourselves. All right. Awesome. Example. Okay, this is not lecture-ish anymore. This is just an example disembodied from the rest of those examples, but it's still indeterminate form. Suppose we want the limit as x approaches pi from the left. I will have no chalk left soon. Of 1 minus cos x over sine x. You guys know about Zeno's paradox? You know about that thing? Where to reach for me to get there, right? I have to cross half the distance. I have to cross half the distance, and so I'll never get there. Which is what the chalk reminds me of. Eventually, I will have no chalk left. In the limit. Anywho, that's good. I'm just talking to myself. I might as well just. Okay. We want that limit. Okay? So, what do I do? It's L'Hopital time. So let's use L'Hopital's rule. See what happens. What happens? What's the derivative of the top? 1 becomes 0, minus cos becomes sine. It's the bottom, becomes cos. All right. As I approach pi from the left, what is sine doing? It's approaching 0 from above, which I think won't matter here. Okay. Okay, again, as I approach pi from the left, I'm approaching 0 from above. And again, the above probably doesn't matter here. As I approach pi from the left, cos is approaching minus 0. Minus 1 minus 0, minus 1. Okay, as I approach pi from the left, cos is approaching minus 1. So what do? I say, well, that's pretty good. Use limit laws, and I write 0. 0 over minus 1 is 0. And everything's good, right? Can you see? Okay, I approached pi from the left. And I said the limit was 0. That's not 0. Right? What did I do wrong? There's something I always write, and I didn't write it this time. And what's that? Okay. What do I always say? I always say check. Yes, ma'am.
The derivative is minus sine.
Derivative of cos is minus sine, but then minus cos becomes, yeah? Yeah.
You had check if you could use it?
Yeah, and I didn't, and I couldn't. Okay? Okay, so L'Hopital was not cool here, and I did it anyway, and now I'm screwed. Okay? So this is bad. Okay? Because what happens as x approaches pi from the left? Where's this guy going? Well, cos, we already talked about this, cos is going to minus 1. So 1 minus minus 1 is 2, so this top bit was going to 2. Okay, as I approach pi from the left, sine is approaching 0 from above. That's none of the indeterminate forms. I have no right to use L'Hopital. That's why it went wrong. Okay? Math always works if you follow the rules. Okay. Anyway, what was going on here? The top was going to 2, the bottom was going to 0 through positive values, so the actual answer was infinity. Hey, look. Okay? Okay. Now, if I'd asked for the limit as you approach something else, as you approach, let's say, 2 pi from the left, okay? As you approach 2 pi from the left, what's going on? Sine is approaching 0. Cos is approaching 1, and so minus cos is approaching 0. And so you've got 0 over 0, and there you could use L'Hopital. Okay? So if I was asking for this limit, or this limit, L'Hopital would have been fine. It would have been 0 over 0. I had every right to use L'Hopital. I would have gotten this. I would have seen what would happen, and I would have had a 0 up here and a 1 down here, I hope. I'd have a 0 there and a 1 there, and I'd have gotten a 0, and it would have been fine. That would have been the right answer there. Okay? But here, it wasn't the right answer, because I did not have an indeterminate form that L'Hopital liked. Okay? Yes, ma'am?
You were saying how if you have like an indeterminate type of infinity minus infinity, if infinity has the same sign,
Mhm.
what if the infinities have different signs?
I want to say that if you've got something that looks like, you know, how do I put this? So if you've got like an F, okay, suppose that guy's blowing up and that guy's blowing down. That guy's blowing up, that guy's blowing down. Okay, so you get something that's growing without bound and you subtract something that's decreasing without bound, it would make sense to say the whole thing is growing without bound, yeah?
Yeah.
Yeah.
Okay.
So if they're the same, yeah, so there was only really a tug of war if they're the same kind of infinity and you're trying to subtract them. Is that fair?
Okay.
Yeah. Cool? Thank you. Okay. Excellent. Good. Okay, one more of this indeterminate stuff and then we'll do something else. This one's very, very short. I don't know how much of this you can expect to see. The limit as x goes to infinity of x sine 1 over x. Awesome. Okay. All right, what's going on here? As x goes to infinity, x goes to infinity. As x goes to infinity, 1 over x is going towards 0, so sine is going towards 0. Indeterminate product of type 0 times infinity. So I try to do something with it. And one thing you can do with it is this. I said substitution was one of the things you could do, so here's substitution. I have a feeling I said substitution for differences, but whatever. So yeah, you can use substitution. Let h equal 1 over x. Okay? Now what? Then, x going to infinity is equivalent to, or the same as, h going to 0 from the right. Okay, as x grows without bound, this guy goes down towards 0. Cool. All right, so let's rewrite this guy as this. Limit as h goes to 0 from the right of, h is 1 over x, so x is 1 over h. 1 over h times sine h. Okay, not hyperbolic sign. And life's about to look good. That's a quotient. Yeah, I could have written it like this. As h goes to 0, that guy's going to 0, that guy's going to 0. 0 over 0. And we've seen this before anyway. We know that the limit of sine x over x as x approaches 0 is 1. Life's good. And you will note that as I go this way, I'm approaching 1. Okay? All right. Awesome. Quick note. I'm not going to do these examples, but you've seen things like this before. The limit as x grows of something like 3x squared plus random stuff over, let's say, 2x squared plus other random stuff. Whatever. Okay, you know what to do. You divide top and bottom by the highest power you see in the denominator. Then you use limit laws or whatever you want. Not whatever you want, use limit laws. to find out the answer is 3 over 2. Okay? But you could also say, well, look, the top is going to infinity and the bottom is going to infinity, so I could use L'Hopital's rule here. Okay? And I think you wind up using it twice. Is that a question?
Yeah, I'm just confused as to why the last example the answer was 1.
I could say, okay. You can use L'Hopital and get cos and 1. And if I start here, is that good enough, or do you want to start here?
After.
Like here?
Yeah.
Yeah, okay, so you can use L'Hopital here because it's 0 over 0, and so you've got cos over 1. And it's good. Cool? Yeah, or just today's stuff, whatever, yeah. Yeah, again, or from memory. Okay, so you can say both those guys blow up, you got infinity over infinity, I can use L'Hopital, I'll apply it twice in sequence, and I'll get the answer to that, okay? So it's a question for you, would you rather do that, or would you rather do the division thing? Okay, whatever's easier and more appropriate. Okay, so sometimes L'Hopital is possible, but perhaps you don't want to do it, and there's another way that's nicer. Another example like that is this one. Okay, as I go toward 2, this guy's going toward 0, this guy's going toward 0. So you could say, well, it's indeterminate 0 over 0, so I could use L'Hopital. Okay? Possibly twice? Not twice, I think once is enough. Okay, use L'Hopital once and you got your answer. Or, what can you do? You can just factor the top, do the division, and you got your answer that way. Okay, so whatever you feel like doing. So that's it. Only use L'Hopital when you're allowed, and when even when you're allowed, sometimes you might not want to use it. Okay. Okay, we talked about Newton's method again, and you asked me, why would I do this if I've got a calculator? Which is exactly the right question to ask. So we'll do a more interesting example. And now I will possibly yield to you guys again. Okay, we're going to make up a function, we're going to solve it. Okay. Utah. All right. Do I just make something up? I can make something up. Here, let's do cos. All right, pick a number. A nice small integer.
3.
Thank you. Let's say minus, pick another one.
7.
Okay, you said 5. What did you say?
7.
Excellent, we'll do 1 plus 5. Sine. I have no idea what this is going to do. Okay. And give me one last one.
34.
Okay, 13 and 4. All right, suppose we're trying to solve this thing for some sick reason. The point is that your calculator won't do this in one step. Computer's freaking out right now. 7 plus 13x to the 4. A second team. And it's got no zeros. That's nice. Let's do my team. Minus 13. Good enough. Okay. Okay, it's incredibly uninteresting. Let's see if I can make you see this. Nice. What it's done is it's now made my screen smaller and not projected anything. So that's pretty good. Anywho, okay, we're going to find the zero of this thing, or a zero of this thing. You can't see it at all, huh? Duplicate it. Okay, to hell with it. Here's what's going to happen. If you've got a computer or some sort of Desmosable thing, use that. But I will show you roughly what this looks like. Okay, this looks like this. This might be solvable, but I'm just, too thick to do it maybe. Okay, it looks something like that. That's 1, somewhere around minus 0.5, and somewhere around 0.5, okay, ish. We're hitting the x-axis. So let's try to find one of those roots, yeah? Okay. Okay, so what do we need for Newton's method? We need an initial guess. What's our initial guess? What's a smart one? 1/2, minus 1/2, one of those things. Okay, so let's make our initial guess 0.5. Okay? Again, you could find that using just logic somehow, or just a blind guess, or you could use IVT, or you could use bisection to get within a reasonable place and then start using Newton's method. Or you could draw a sketch or a graph and see where it looks like you're crossing. It looks like I'm crossing somewhere around 0.5, so I'll write that. Cool? All right. So, this is my function. The zeros I'm trying to find. Let's find its derivative. Okay. This was a very bad idea. Okay, cos becomes minus sine. X cubed minus 5 sine x to the 7. Good. Times 3x squared minus 5 cos x to the 7 times 7x to the 6. Maybe consider not writing this down. Minus whatever 4 times 13 is, x to the 3. Someone want to tell me if that's wrong? And I'll use the genius of the computer to figure this out. Okay. So here we go. Cos, and you can't see any of this, I'm sorry. Cos x cubed minus 5 times sine. By the way, if you guys vote me to do something else, I'll do something else. X to the 7 minus 13x to the 4. Cos x cubed minus 5 sine 7 minus 13x. Okay, derivative. Minus sine. Just keep yourselves busy. Minus 5 times sine x to the 7. Times 3 x squared. And you're going, how is this easy? Minus 5 times cos. Times. I'm done. Okay, it's over. You'll be good if this is one of those cases that doesn't work. Minus. Okay. Awesome. Okay, I think. Okay, good, here we go. All right, so our initial guess was what? It'd be good if I look up and none of you are here. Okay, so we started at 0.5. Okay, and we iterate. Okay, so what's our iteration? We go that guy minus f at that guy over f prime at that guy. That's it, okay? And we get this. Seriously, if this doesn't work, I'm going to be really angry. Okay. Roughly. Okay, suppose I said do this to I don't know, 5 decimal places, or 5 significant figures. Okay. So 0.5282027. 0.5282027. 0.5282027. Stuff. Okay. Do it again. Okay? So now I use x2. I go x2 minus f at x2 over f prime at x2. And I get x3. x3 is equal to something. 0.526120. 0.526120. Something. x4. 0.5261086. Something. Have I got enough? No. Okay? And again, at each step, make sure, see how many significant digits agree with the next guy. Okay, so here, only the first guy agrees. Okay? Here, these two guys agree. Right. Here, these four guys agree. Okay? So I reckon, in one more step, I'll be done. Okay, if you can't see, we'll do x5 here. x5 is equal to 0.526, 108, 6. Okay, and you compare those guys, it's looking pretty good. Okay, so each time draw a little sausage or something, drawing which ones have settled, and once you have enough, you've got enough. And I said 5 significant digits, we're already better than that. Okay, so you can stop there, round it off if you want, and say that that's the answer. Okay? That's it. And it looks right. Take my word for it. Okay? I hope that was mildly informative. So someone asked me to do this for bisection, so I figured I'd do it for this. Okay? All right. Questions? Sounds, anything? Grunt at me or something? And remember what I said? I said that you double the number of good digits you have each time? Yeah, it's pretty much happening, right? We had 1, then 2, then 4, then possibly 8. Okay, so it goes quite fast. Bisection doesn't go that fast. All right. All right, excellent. Okay, what do we got? Almost had a heart attack. I thought it was 7:23. I used to not change any of my clocks until the next round of DST came along. So that's something you can do. Okay. Any questions? Ask me anything you want, obviously. Okay. Someone asked me this. I'm not going to talk about this too much, but someone asked me about implicit differentiation. I've just lost the thing completely now. Is that right? So, okay. Okay, someone asked me about implicit differentiation. They said, I don't know why we're doing this, and I'm not entirely sure what you meant, and you did it anonymously, so I can't talk to you. Anyway, so I don't know what you meant. If you want, let me know. Until then, I'll just say where we use this, okay? And you don't have to write any of this down. But, what are we talking about? When we have the rate of change, or we want the rate of change, okay, of a function that's implicitly described. Again, we've seen all of these, I'm just summing up. Okay, so if you've got something that is a function and it's implicitly described and you want essentially the rate of change, then obviously you do this, rather than trying to write it explicitly, because that might be worse. Or you just want a slope. Given an equation that relates x and y implicitly. Okay, which is pretty much what I've always been showing you. I give you this great big ugly thing and I say, okay, I want the slope at 1, 2, and this is what you do, right? Maybe you're looking for tangents or normals, and a normal is something that's perpendicular to a tangent, in lenses or trajectories. Now, if I can get this thing working again, I'll show you something. Let me try turning it off and on again. Good enough? Okay. You can see, right? Yeah. Okay. So, this was somewhere. Of course, you can't read any of it, apart from the title, which is meant to be inflammatory. Remember we talked about there's a dragon that's taking your shield away. This is meant to be the continuation of that example. After just barely surviving the attack, the dragon is momentarily fatigued and stops to catch its breath. This is your chance. You get out your sling, load up a rock, and start swinging it in a great ellipse in the horizontal XY plane given by that. Where A is 5 meters and B is 4 meters. To knock out the dragon, you must hit it in the head. If its head is located at 25 thirds 0, then at what coordinates on the ellipse did you let the rock go? Whatever, okay? All right, the point is, if you've got a trajectory and you release something at some point in the trajectory, you fly off on a tangent, okay? And so this is an example of that. And if you want, I can solve this for you, so let me know if you want me to do this, or you can try this on your own, okay? The question is, where do you have to release the rock so that it hits that guy, okay? As far as I know, you don't normally find tangents and trajectories like this. You normally, write the thing out with parametric equations and do it that way, but whatever, this also works, okay? So essentially you can write some sort of, a formula or something for the slope of the tangent here, and then arrange things such that from there to there you get that slope, and so you hit the guy in the head, okay? Again, silly example, but you do have trajectories of like orbiting planets and that kind of thing, okay? And if something gets released in a trajectory for whatever reason, then it goes off on a tangent. Or if you want to talk about the velocity of something that's going in a trajectory, that's on a tangent. Okay. And again, if you've got lenses and you don't want to talk about optics, then you talk about normals. Okay, we talked about two other things. We talked about logarithmic differentiation, okay, which I will say again was an optional topic, but makes things very nice sometimes. And we talked about derivatives of inverse functions. Okay, so we found the derivative of arctan and ln and these kinds of things, okay, using implicit differentiation. So it's useful for that. And finally, sort of related rates. Okay, so some people would say that when you're doing a related rates problem and you've got something like v equals 4/3 pi r cubed, and then you take the derivative with respect to time, some people call that implicit differentiation, so you might think of that as an application as well. Okay, so that's my attempt at answering your question why. Okay. Now, guys, please protest loudly if I'm doing things you don't want me to be doing. Okay. Now, I mentioned robots and pendulums and springs and stuff, and I felt I might be upsetting you, so now I'm going to upset you with an example that's more relevant. And this is what I did in grad school. You can tell it looks like engineering, even though it's about biology. Okay, so what my job was, I'm very briefly going to talk about this just to give you some kind of example that has something to do with biology. Okay, my job was to see why some people, how do I put this? The control system for their breathing is out of whack, okay? And so the breathing goes nuts, quote unquote. And so periodically they stop breathing, okay? Which is called apnea, okay? Or the periods of no breathing are called apnea. Okay, and so this is meant to be a model of the system, okay? So up there are models of gas exchange, so what's going on with your lungs. And what's going on down here is the control, okay? So what are the two relevant variables here? That phi A thing up there is meant to be ventilation, alveolar ventilation, which is how much fresh air you bring into your system per unit time. And those P's, okay, are partial pressures, or you can think of levels of carbon dioxide, let's say, in your blood. Okay, so when your brain sees that you've got a lot of carbon dioxide in your blood, it says breathe faster, okay, or breathe harder. Okay, if you've got a lot of CO2 in your blood, your brain says breathe harder so that we can get rid of this, okay, and bring in more fresh air. As you bring in that fresh air, that phi A increases, okay, and the level of carbon dioxide in your blood goes down. Okay, so you've got a closed loop system here, okay. feedback. Okay. Excellent. Okay, so part of this is modeling gas exchange in the lung. And look, a differential equation. Okay? What are we talking about? We're talking about the rate of change of the level of carbon dioxide in your blood. Okay? So that's that rate of change. Okay? And it's a differential equation because we've got that derivative and we've got the variable there, and we've also got another variable there, which is something you don't see. Okay? So again, we've got a variable and its derivative and some other stuff. That makes a differential equation. Okay? I promise I won't talk much longer about this. But basically, here's what you're doing. You've got blood coming in and blood going out at a rate Q, which is called cardiac output. Okay? The blood's going into your lungs or around your lungs in the capillaries. It's entering at some concentration and it's leaving at some partial pressure. Fresh air is coming in and bad air is leaving. The bad air has this partial pressure of carbon dioxide, and the stuff coming in has this partial pressure of carbon dioxide. And as I said, the rate at which this is happening is alveolar ventilation, which you'll hear about later in some course, physiology, if you haven't heard about it already. Okay, and this is gas exchange. Okay, and if I do a conservation of mass thing in that box, okay, then I can write a differential equation for this. And that's the differential equation for that. Okay, so I can model all the pieces of my system using relatively simple models to describe what's going on and possibly analyze, under what situations the things would go out of whack. Okay, and I promised linearization, and here's linearization. Okay, there are tools that you can only use for linear systems, I mentioned. Okay, called Laplace transforms, which involve integrals. There's tools you can only use for linear systems. So that thing that I just showed you is not linear. Okay, so you have to linearize it somehow. And this is what you do. It's exactly the stuff you've seen before. I want to consider the behavior of the system in the vicinity of any whatever operating point, which is exactly what you guys are doing. Close to an operating point, you want to see what the thing looks like. Okay? I take derivatives at the operating point, which is exactly what you guys do, except notice my sexy slanted curly D's. Okay? And those are there because I've got more than one variable kicking around. And so I say that model I had is approximated by its linearization about the operating point for sufficiently small excursions, and then I write that, and that's my linearized model. Okay? I hope that qualifies as proof that you can use this for stuff other than springs. Okay? Okay. Again, that's a model of gas exchange, written as a differential equation, and linearized, so we can analyze it using the kind of tools we know about. Okay? Okay. Now what? Okay, this again, someone asked me to do this, so I will do this. Okay, any questions about this? Awesome. Again, if you haven't seen this stuff, you will see this stuff, except probably not written as a DE, because I imagine the physiology instructors don't do that kind of thing. Okay. All right, related rates. And somebody asked me to do an example related to the project, and I'm not very creative, so I've just taken the project question, and I'm going to do that for you. Okay? Okay, this is the project I think almost none of you did, if not none of you. It's project 2B. And by the way, I'm trying to point out as we go that the other projects were relevant, right? So for instance, that whole difference quotient thing was relevant because sometimes the computer has to approximate a derivative, and that might be how it does it. And for the Taylor polynomial thing, oodles of applications. All right. So there's our puppy there. A sector, and a sector is a pie slice, right? In a circle of radius r comprises the triangle T and the region S drawn there. Suppose that the radius vector rotates counterclockwise, or you can think that point P rotates counterclockwise, with angular velocity, and angular velocity is the rate of change of that angle which is a constant. Show that the area of the sector changes at a constant rate. Okay, so the area of that pie slice changes at a constant rate. Yeah. Trying to see if there's an easy. Okay. Never mind. But then neither the area of T nor the area of S changes at a constant rate. Okay, so the pie slice grows in area at a constant rate, but neither T or S do. Okay? Okay. Green visible? Okay. Okay, so nothing too hard about this, okay? All right. Let A represent the area of the sector. The sector. And I'll say AT because it's the area times T. Okay? All right. So, does anyone know the formula for the area of a sector? Because I don't. Okay. At one point I memorized this. Okay, what is that area? How big is that pie slice? The pie slice compared to the entire circle, okay, so the entire circle is 2 pi radians, right? That pie slice is theta radians. Okay, so theta over 2 pi times the area of the circle. Okay? The area of the circle is pi r squared, and this pi slice covers theta over 2 pi then. Okay? Let me know if that doesn't make sense. Cancel, cancel. 1/2 r squared theta. Theta t. Theta t. Okay, again, that point's going around, theta's changing. Okay? All right, we can probably easily see already at this point, this thing is a linear function of theta, and that's the reason the next thing is going to happen. Okay, the rate of change of the area of the sector is just the derivative with respect to time of this thing. Okay? What have we done? We've written an equation relating A to theta, and using that, we're going to relate their rates. It's the easiest possible thing. 1/2 r squared d theta dt. Okay? It's the kind of related rates you hope for. Okay, and I said d theta dt was just omega, which is a constant. We wind up with this. And that is indeed constant. Okay, the area of the sector grows at a constant rate. Does that make sense? All right. Okay, we have the area of that triangle now. Okay, let A sub t denote area of the triangle. Okay, how do we find the area of that thing? We got r theta. Someone want to tell me? I think when I was in high school I knew a formula for this. Or tell me it's height, or a height. My way is stupid. Yes, ma'am.
Like base times height over 2.
Good. And how would you get the height? Or which height would you go for?
The height would be, I think like 1/2 cos over r. 1/2 cos theta over r, something like that.
Okay, and that's what? That's yeah. I'll look at this. This is from a.
I did this project and that's
Okay.
how I did it.
Okay,
so
fair
tell me
enough,
it's
fair
wrong.
No, I'll show you the way he does, and then I'll show you the dumber way I do it, and yeah. Okay, so if you treat that as the base and you treat that as the height, okay. What have you got here? What's the sine of this? The sine of this is opposite over hypotenuse. Okay, so sine of theta is thing. Okay, we'll call this h. H over no, it's not good. Hey, to hell with it. We'll call it h. H over r. Okay, sine is opposite over hypotenuse. Okay, so h is r sine theta. And that's it. Okay, And if you do enough of these kinds of things, or you take physics and you'll see a lot of these kinds of things, you'll just write r sine theta and you'll see that that's that. Okay, and so the area of this thing is 1/2 base times height, the base being r, the height being that thing. Okay, 1/2 r squared sine theta t. Okay. All right, makes sense? Half base times height. Okay, now I'll just tell you, because I like to confess things like this, I'm a bit too thick to have done it that way, so what I did was this crazy thing. I said, it's an isosceles triangle, I'll do this. Okay, what do we got? Each of those being theta over 2, so I bisected that thing, and then I bisected this thing. Then what have we got? This guy is r sine theta. This thing is r cos theta. Sorry, theta over 2 and theta over 2. Okay? Bisect, bisect, and you get this. Okay? And so what's the area? It's 1/2 base times height. 1/2 of the base is this. So r sine theta over 2 times the height, r cos theta over 2, which is r squared times sine times cos. Okay? And you can use the double angle formula to write it like that. Yeah?
What were you trying to find for there?
Here, where? Here? Here?
Yeah, like just.
We're trying to find the area of the triangle.
Okay.
And I said that's a straightforward way, but you can also do it my dumb way, is what I was saying. Yeah? Is that?
That's what I did.
Yeah. I like it then. Good? Okay, yeah, you said cos, so I figured maybe that was involved. Yeah, that's how I've been doing it for a while. Okay, so good. You can just rewrite that as that, and that's cool. Okay? You get the same answer. And all we were asking was, what's the rate of change of this thing? 1/2 r squared. Okay, now we have a more interesting thing, right? We have to take the derivative of this, chain rule, cos theta. Again, remember chain rule, so times d theta dt. Okay, and we said again, this thing is just omega. Okay? And to be quite obvious to you, this thing is not constant. Okay? That's constant, that's constant, that's constant. Theta better be changing. Cos theta is changing. It's not constant as promised. Okay? Where is anything? Okay. Good, so that tells you that the area of the sector is changing at a constant rate. The area of the sector is changing at a constant rate. The area of the triangle is changing at a not constant rate. Okay? And so as far as I'm concerned at that point, okay, if we call the area of S A sub S, you know that that's whatever's left. Okay? And you could do this. You could say this. You could say, take the derivatives everywhere with respect to time. Okay? Well, what did we see? We saw that was a constant. We saw that that was not a constant. So it makes perfect sense to say that's not a constant. Okay? You could do that. Or you could write the expression for this, take the derivative. Okay? Or you could take this guy and this guy, subtract them, and write that. Okay? Some way or another, you're going to see that that's not constant either. Okay? So that's it. The sector is increasing in area at a constant rate, but the other two guys are not. Typically. What do we got, 6 minutes, 5 minutes? Guess what I'm gonna do? One more. Okay, this is none of those stereotypical related rates questions. Any questions about this or anything that I've miswritten or missaid? Okay. Okay, is that thing up there? Good. I'll try to do this quite quickly. so that no one understands any of it. Conical tank. Okay, so what do we got? We've got a totally normal water tank in the shape of a cone. Okay, with water in it. Okay, good. The height of this thing is what? It's 10 meters? Okay, we've got height 10 meters. And base radius 4 meters, I think. Awesome. Okay? Now, we're trying to see if water's draining from this thing at 5 meters cubed per minute, just because I didn't feel like saying liters and making anyone convert anything. We want to know how fast the water level is dropping when the water is 6 meters deep. Okay? So let's call the depth of the water h. Let's call the radius of this surface circle thing r. Okay? Excellent. So now what do we want? We know we're given, possibly at an instant, doesn't really matter. We're given at an instant the fact that what? The volume of water left in this thing, so let's call the volume in here V. Okay, we'll call the volume in there V. The volume of water is decreasing. Decreasing at 5 meters cubed per minute. Okay? All my linear dimensions are going to be in meters, all my times are going to be in minutes. Okay. Okay, so whether at that instant or for all time, the volume is changing at -5. Okay? Don't get those signs screwed up, although you should be able to see in many cases when you have. Okay, at the instant we care about, what's happening? The water is 6 meters deep. And what we want is to know what? We want to know how fast is the water level changing at that instant. Okay? All right. Nothing complicated here, provided you know the formula for the volume, which if you need it, we'll give you. Okay? What's the volume of a cone? 1/3 pi r squared h. Okay. Okay, there's our relationship. Now, r is changing as the water falls, and h is changing as the water falls. Okay? It would be quite nice if we just wrote this whole thing in terms of h, which is the thing we care about, and then took derivatives. That would make life easier. Okay? So we could draw triangles. Okay? So consider the cross section of this thing and look at that half of it. Okay? So that's h. That I think is 10. That's 4. And that's r. Okay? Well, is it? Yeah, good. Okay. We use similar triangles. These triangles are similar, however you want to think about it. They're both right angles. Those angles matched by that parallel thing. No, this angle is common and those two are right angles. So these are similar triangles. Okay, so 4 over 10. 4 over 10 is equal to r over h. Okay, what are we trying to do? We're trying to eliminate r, okay? Because it's a nuisance. Okay. So what do we get out of this? R is equal to 2/5 of h. Okay? And then we can throw that in there. Again, a warning, never, ever, ever substitute instantaneous stuff in, especially that kind of thing. Never, ever, ever plug that guy in until you've taken the derivative. All right, what do we got? Something hideous, 25, 75 on the bottom, 4 on the top, 4 pi over 75, possibly h cubed. Excellent. Okay, and this thing is always true. Okay? This thing. Okay, good. Now we can just take the derivative. Okay, derivative of both sides with respect to t, as we always do for related rates, and we'll have our answer in no time. Differentiate both sides with respect to time. Okay, dv dt, easy peasy. Constant over there, 4 pi over 75. Derivative of this guy with respect to time, 3h squared. Don't forget chain rule, 3h squared dh dt. Okay, and I can rewrite that as 4 pi over 25 h squared dh dt. Okay. Now I'm free to plug in, okay? At the instant I cared about, the depth of the water was 6, okay? So now we can sub in. So at the instant we care about, 4 pi over 25, 6 squared dh dt, and dv dt is minus 5. Minus 5. Okay, and then you just solve. dh over dt is equal to approximately minus 0.276 meters per minute. There we go. Okay, make sure the units make sense. It makes sense that it's negative, this thing is falling. That's all good. What else? Notice this is just at that instant, okay? As this thing changes, that rate will change, okay? And if you like, you can see how that depends on h. The only other thing I'll say here is this. We chose the path of trying to eliminate r in this thing, okay? You could have not done that. You could have just gone here and just right away taken derivatives with respect to time. You would have wound up with a dr by dt and a dh by dt, okay? And then you'd have to relate those rates and find r and then go that way. Does that make any sense? No? Okay. So okay, should I write this? Okay, I'll write this real quick, okay? You could write, at this point, dv dt is 1/3 pi, okay? This is the bad way of doing this, okay? Okay, what's this guy? Derivative of first times second plus first times derivative of second. Okay, you could have done that, okay? And then what would you have needed? Not only would you have needed dh dt, but you would have needed dr dt, okay? And you would have needed r, okay? This is more work, okay? So life was made better in this case by eliminating r, having just one variable, simplifying stuff, and taking the derivative. This is totally doable, but is more of a pain, okay? I think that's it. 2r da-da-da-da-da. Okay. That's it, everybody. Thank you very much. Have a very pleasant evening. If you've got any questions, come talk to me.